Hello and welcome back. In today's video we are going to cover coefficient of compressibility, another fluid property that we need in the subject. The topics covered will be density and volume dependence on pressure and temperature, how density or specific volume depends on temperature and pressure, and that will lead to us to what is kappa or what is coefficient of compressibility. Then we will move on to relation of coefficient of compressibility, how is kappa related to P and T mathematically. Then kappa for liquids and water, an example. After that we will move on to a phenomenon that is shown by the dependence of density or volume on pressure. This dependence results in a natural phenomenon called water hammer, and we will move on to how coefficient of compressibility, what is coefficient of compressibility of an ideal gas, and what is isothermal compressibility, which is also related to kappa. So let us begin. Now first of all, rho dependence of specific volume or density on pressure and temperature. We know, for example, if we have a solid and we apply force or pressure on this solid, and the volume of the solid changes, there occurs change in volume, and these two, whether this force or pressure related to this volume change or length change, this is related by Young's modulus of elasticity. Young's modulus of elasticity. Similarly, in case of fluids, we have this volume, or it is reciprocal density. It depends on pressure as well, and it depends on temperature. As I have talked about this in previous videos, that density change or pressure or volume change occurs due to change in pressure and temperature of a fluid. So if we talk about change in volume due to pressure, that is equivalent to this solid is, we are applying a force on a solid and it deforms, and that relation between this stress developed due to force and this strain induced due to the change in the dimension, the relation is given by the Young's modulus of elasticity E. Similarly, if instead of solid this is a fluid, liquid or a gas, and we apply pressure, the volume also changes. With increase in pressure, volume decreases generally, and with decrease in pressure, volume increases. So we have to have a relation between this pressure change due to the pressure change and this volume change, and volume change is accompanied by the density change in density. So then if volume decreases, density increases. If volume increases, density decreases. So these two changes will be inversely related to each other. So in first case, we want to know what is the effect of pressure on volume, and we know that increase in pressure generally decreases volume or increases density. Now what about temperature? Now if we increase temperature, volume increases generally because the kinetic energy of the molecules increases. Molecules move at higher speeds, so they want to go apart from each other. So with increase in temperature, volume of the fluid increases. If volume of the fluid increases, that means density will decrease. So we know the dependence of density or volume on pressure and temperature. Now we need to relate this pressure change with the volume change, and also we need to relate the temperature change with the volume change. When we relate pressure change with the volume change, it leads to coefficient of compressibility. So we have a property called kappa that gives us how pressure changes the volume or density. And when we talk about temperature changes, when temperature changes, how volume changes. So that is given by another property called beta, denoted by beta, which is called coefficient of volume expansion. So if we want to know what is the effect of pressure on volume or density, it is quantified by a property called coefficient of compressibility. And if we want to know how much density or volume changes when we change temperature. That is quantified by another property denoted by beta, called the coefficient of volume expansion. So we'll talk about coefficient of volume expansion in a different video in detail. Let's move on to this section. What is kappa? That means dependence of rho or V on P only. Now, as I said, the relation of force applied on a body to the stress induced in the body is given by Young's modulus. Similarly, effect of pressure on a fluid on the volume change of the fluid is denoted by a property called coefficient of compressibility, denoted by kappa. So how it is this related? Kappa is mathematically exactly equal to negative specific volume dou P divided by dou V at constant T. Why? Because we want to know what is the effect of pressure only, keeping the temperature constant, because if temperature also changes, volume change will occur partly due to pressure and partly due to temperature. So we want to keep the temperature constant, so we get the effect of only pressure. So change in volume because of the change in pressure. This is the exact relation of pressure and volume, and these two are related by a property kappa, coefficient of compressibility. Why negative sign? Because increase in pressure causes decrease in volume. But if we replace V by density, so there will not be minus sign, because increase in pressure increases density. So increase. So, or we can say in terms of density, it is rho dou P by dou rho at constant temperature. So these are the two relations of coefficient of compressibility that relate us how pressure change causes change in volume or density. It decreases volume or it increases density. Now these are the exact differential relations, Now for numerical purposes, we use the approximate relations, and those approximate relations are kappa is approximately equal to minus delta P, finite change in pressure, divided by delta V by V, divided by relative change in volume, or in terms of density, this coefficient of compressibility is approximately given in finite change. It is delta P divided by plus sign in case of density, delta rho by rho, relative change in density at constant temperature. T is constant in both the cases. So this is how change in pressure is related to change in volume or change in density through coefficient of compressibility. So coefficient of compressibility basically gives us a way to quantify how much volume change or density change occurs when we change pressure. So relation of kappa. Next is kappa for liquids and water. Now we know if we compare two fluids, liquids and gases, we know if we apply pressure on liquid, the volume change is very, very small. It's almost negligible. And in case of gas, it is very significant. It is large. The volume changes by large amount. But in case of liquids, it is we have to apply a large amount of pressure to cause small change in volume, which means this has to be very large in order to cause the small change in this, which means when numerator is large, this will be large. When denominator is small, this will again be more large, or this will be larger, which means for liquids kappa is much greater than 1. It is larger. And for gases it will be smaller, because small amount of pressure is needed to cause some change in volume, to cause significant change in volume. So in short, kappa for liquids is very large as compared to kappa for gases will be smaller. For example, if we take the example of water, if we take water at atmospheric condition, normal atmospheric condition 1 atm, and want to apply pressure on it so that 1% volume change occurs or 1% density change occurs for water. For that we have to increase pressure from 1 atmosphere to 210 atmosphere This is how large pressure has to be increased for water in order to cause 1% change in volume of water or density of water, which means the kappa for water becomes, because of this percent, it becomes 21000 atmosphere. Because if we see here, units of volume will be cancelled with this units of volume, and the unit for kappa will be same as the unit of pressure. So kappa for water, to make kappa for water is 21,000 atmosphere. This is very large. Next is a phenomenon shown by dependence of density or volume on pressure. There's a natural phenomenon that arises because the density of water changes or volume of water changes due to the change in pressure. Even if it is very small change in pressure, it still shows a interesting phenomenon. And one such phenomenon is water hammer. And what is water hammer? Water hammers, for example, we have a piping network or piping system where we have elbows, we have valves and all that. Suppose water is coming in this direction, we have a valve and we open this valve. Water flows. Water keeps on flowing smoothly through this pipe. What happens if we suddenly close this valve? What happens if we suddenly close this valve? All this running water, running at a high speed, it suddenly comes rest at this point. So what will happen if water is coming suddenly at this comes suddenly to rest at a point? So what will happen? It will start vibrate, because when it is moving at higher speed, it suddenly comes at rest. So because of that high pressure, it will compress by that small amount. It will compress. That compression will be followed by expansion, then compression, expansion. So a wave will be formed at this point. Wave will be formed, and this wave will travel in all directions. And when this wave, acoustic wave, hits or reflects from this surface of the pipe, it creates a sound. And that sound is similar like we are hammering. We are taking a hammer in our hand and we are hitting the pipe with the hammer. The sound that is produced at that time is the sound similarly produced when this wave hits this surface. That's why it's called water hammer. Now, this is one consequence of this phenomenon, water hammer, that it produces this hammering sound. Another consequence is that these waves, when they strike these surfaces, these elbows and these mountings, what will happen? They are destructive. They can cause leaks at these places and they can destroy this networking system. This is called water hammer. This phenomenon occurs because when high speed water suddenly stops, it compresses at that point, and that leads to the generation of acoustic wave, which causes this sound and this destruction of this piping network. So it is basically a consequence of dependence of volume on pressure. Now, how can we avoid this water hammer? One way to avoid water hammer is that we practically use we use a device called water hammer arrestor. Water hammer arrestor, which is basically a volumetric chamber that has a flexible device in it that can absorb this wave. So it will be something like here. And this wave absorbing device may be piston. So suppose there is a piston inside. What will happen is, when water comes quickly in this direction at high speed, and we suddenly close the valve, the wave gets generated and that wave flows upwards and that moves the piston. So basically that moving piston absorbs that shock wave, and that wave does not travel to the surrounding wave. The effect of the wave on the surrounding walls will be a minimum, and because almost entire shock of the wave is absorbed by this piston. This is called water hammer arrestor. Now this water hammer sound here is like what is coming next. next is coefficient of compressibility of an ideal gas. We know for an ideal gas P is equal to rho RT, ideal gas equation of state, and if we differentiate P with respect to rho, dou P by dou rho at constant temperature, assuming temperature is constant, we get R is already constant, T R we are assuming T constant, so it will be RT. But from the definition of coefficient of compressibility, it is rho dou P by dou rho at T. From the definition which I showed before. So we will replace this by RT. So kappa will be rho RT, but RT is equal to P by rho from the ideal gas equation. So we can write a rho P by rho. So rho gets cancelled, which means kappa for an ideal gas is simply the absolute pressure, which means for any fluid, liquid or gas, kappa is approximately rho, or we can write it delta P delta rho by rho for any fluid, liquid or gas. But specifically for ideal gas, it is basically exactly equal to the absolute pressure. Now, one more thing, since kappa is equal to delta P delta rho by rho, and we know for ideal gas kappa is P, so we'll replace kappa by P, so we will get P equals delta P divided by delta rho by rho. So we'll take this bracket here and transfer the P on the denominator on the right hand side. So we'll get delta P by P is equal to delta rho divided by rho, which means for an ideal gas, relative change in pressure is equal to relative change in density. This is how we can quantify the amount of change in density due to change in pressure. Relative change in pressure is equal to relative change in density for an ideal gas. Now, last is isothermal compressibility. Isothermal compressibility is nothing but the reciprocal of coefficient of compressibility. That's it. Since coefficient of compressibility is negative V dou P by dou V at constant T, or it is rho dou P by dou rho at constant T. Now, isothermal compressibility denoted by alpha is reciprocal of kappa. That's it. We may use kappa, we may use alpha. They are the same thing, except they are reciprocal of each other. So it will be if we reciprocate this, so it will be minus 1 by V dou V by dou P at T, or in terms of density it will be 1 by rho dou rho by dou P at T. And you can use the approximate relations as minus delta V by V at the numerator divided by delta P, similarly for density. So this was isothermal compressibility. So this was all about today's video, which was about coefficient of compressibility, and the next video we will take another property that is related to change of density because of change in temperature, which leads to coefficient of volume expansion, another property of fluids that will be dealt in another video. Thank you.